We've got one last example to look at here, and again, we're going to set this problem up in our first video, and then we'll go and solve it in our next video. So we have a fence that is built to enclose a rectangular area of 800 square feet. The fence along three sides to be made up of a material that costs $6 per foot. For the fourth side, the material costs $18 per foot. We want to find the dimensions of the rectangle that will allow for the most economical fence to be built. When we say most economical right here, really what we're trying to do, and I'm kind of jumping ahead a little bit here, but most economical really means the cheapest, which in this case we want to minimize the cost, how much it is that we're spending on this fence. So in this case, we've got a rectangular area. I do actually think it would be maybe a little bit helpful to draw out what this looks like. Well, we've got our rectangular fence. It's going to look something like this. So we've got our rectangular fence. I need some variable names for my sides. I'm going to call the long side, how about I call that X? And then the short side of my rectangle, I'm going to call that Y. Now it tells me that, let's see, we know that the fencing along three sides costs $6 per foot. Now it doesn't matter which three sides we pick. So I'm going to pick, let's say the top part costs $6 per foot. Let's say the left-hand side costs $6 per foot, and then the bottom also costs $6 per foot. But then the fourth side costs a little bit more. It costs $18 per foot. So I'm going to say here this right-hand side costs me $18 per foot. So I've kind of hopefully set this up. I want to think ahead next to what is our objective function. What is it that we're trying to optimize here? And we said earlier we want to minimize cost. We want the most economical fence to be built. We want the cheapest fence, which means we want to minimize cost. So let's start thinking about what that cost function would look like. So we want to minimize our cost function. Let's call that C. Now I see four things that this is going to depend on here. We've got one side of our fence that costs $6 per foot. So if I just think about the cost of the top part of this side, well, in this case, it's $6 per foot by X feet. The cost of just that one side would be 6 times X. Now I move over to another side. Let's say I want to look at this left-hand side. Well, that left-hand side costs $6 per foot. I've got Y feet, so 6X plus 6Y. If I want to know the total cost, I probably want to add the cost of these two sides. And I'm going to continue on with that pattern. The cost of that bottom part, well, it's $6 per foot by X feet. So we're going to add another 6X. The one thing that's different here, though, is that right-hand side, remember that costs $18 per foot. And we've got Y feet there, so we're going to add on plus 18Y. So I'm going to just take one step and combine my like variables here, my like terms. C is equal to 12X plus, let's see, 24Y. This is the function that we're going to try to minimize. Now we do have a slight problem here, and that is that we've got our two variables like we've seen before. So I want to try to find some way to write this in terms of a single variable. I'm going to have to find some other relationship between X and Y. I'm going to have to come up with some other equation that relates X and Y. So I'm going to look at what pieces of information have we perhaps not used so far in this problem. Oops. What have we not used in this problem? So we've used, let's see, it's a rectangular, we haven't used this number, this area of 800 square feet. I know that the area of this rectangle has to be 800 square feet. And I can actually find the area of a rectangle. The area of a rectangle is just the base times the height. So in this case, the area would be x times y. So I actually do have another relationship. I know that the area of this rectangle, I can calculate that by finding x times y. And I'm told that that area has to be exactly 800 square feet. So I know that x times y is exactly 800 feet. So I have my area function here. I'm now going to take this other equation that I've solved for, and I'm going to solve it for one of my two variables. Again, just like in that first example, it doesn't really matter whether we solve for x or for y. I'm going to go ahead and solve for y just because that's what I decided right now. So if I want to divide both sides by x, that'll give me y is equal to 800 divided by x. So now I have this relationship between x and y. I can take this equation for y, and I can plug that into my cost function, and then I'll end up with something that's in terms of just that one single variable. It will only be in terms of x. So my cost is equal to 12x plus 24 times y, but we said y is the same as 800 divided by x. So if I wanted to clean this up, I can go ahead and multiply 24 times 800. This is saying c is equal to 12x plus, let's see, 24 times 800. I'm going to get 19,200 divided by, divided by x. This is now the equation that we are going to, in this case, we said minimize here. We want to find the absolute minimum of this function. So I'm just about done setting this up. Before I can wrap this problem up, though, I do want to think about what is the domain of this function. Remember, the domain, that's what values of x make sense for our problem. So what I need to think about is what it is that x represents in this problem. And if I go back and look at my picture, we said x represented the side of a rectangle. It represents a length here. So I think what I would ask first in these types of questions when we're thinking about domain is, could your variable be negative? Could x be negative? So in this case, could I have a negative distance? And to that, my answer is no, absolutely not. It doesn't make sense for us to have a negative. So that means x cannot be negative. The other question that I would ask is, can x be 0 here? Now, if x were 0, that would mean the base, we wouldn't have, the base would be 0 in this case, which means when I multiply those two, I wouldn't get 800, I would get 0. If my x value were 0, I actually wouldn't have a rectangle, I would have an infinitely thin line, which is not the same thing as a rectangle at all. So that means x cannot be negative, and it cannot be 0. So what that means is that x must be positive. X must be a positive number, and the way I would say that then, the domain of this function, we're just going to talk about the set of all positive numbers. So we're going to say 0 to positive infinity, that's all the positive numbers. We are not going to include 0 because we said that if the x value is 0, we'll have an infinitely thin line and we will not have a rectangle. And of course, we can't include negative infinity either. So our domain would be 0 to positive infinity. In this case, we are going to have an open interval. So right now, we have everything that we need in order to finish this problem up in the next video. We're going to go ahead and find our absolute minimum for our objective function, which is 12x plus 19,200 divided by x on the interval 0 to positive infinity.